now we have to worry about programming these devices. What is the mechanics of actually making these GPUs run? I'm going to talk initially about CUDA, which they strung some words together which give us the CUDA acronym, Compute Unified Device Architecture, which are basically 4 words that give you CUDA. It's actually several things. It is a compiler suite, an SDK, a programming language extension to C, a kernel programming language for programming the actual device. And then the SDK, well, the API, the Advanced Programming Interface, will actually allow you to move data backwards and forwards between the device and the host. We'll call this thing the device. The host is your regular computer. And also to execute programs on the device. It's important to notice that it's an asynchronous device. You can allocate arrays on the device using CUDA malloc. So instead of using malloc on the host, or calloc if you're malloc, calloc, or in C++ new, in Fortran. So you can use that to reserve space in the memory on those memory chips on the device. You can use CUDA memcopy to copy data between the host and the device, and that data has to travel across the interface, right? Physically, you have to send bits across this device, across the interface, and back with CUDA memcopy. You're going to queue a task on the device. It's an asynchronous compute device. It's running its own, it's a beat of its own drum, right? It's executing a sequence of kernel tasks. You are adding to its list, its to-do list, right? When you want to run some function on some data, you're basically queuing up that function as a task. And then once the thing is finished cranking on the data, you can copy the data back using CUDA memcopy. So there are three fundamental calls to the CUDA API that you need to really think about, which is CUDA malloc to set up array space, CUDA memcopy to populate and to retrieve data from that array space, and finally, queuing a task. Right? It's pretty straightforward, right? That's one of the reasons I start with CUDA, because it's a fairly straightforward way to interact with the GPU. And collectively, we think of this as an offload model. The host is offloading computational task to the device. Unfortunately, because of the genesis of GPUs for graphics applications, the terminology is just horrible. Terminology is laced with notions of warp, thread, texture, and it's very confusing. Really, we want to think about arrays of threads. We'll preserve thread. We'll think about, we have a notion what a thread is. We've seen it in OpenMP. We've seen it in MPI. We understand a thread. And we'll talk about SIMT groups. Okay. By the way, the analog with weaving, which is where all this terminology comes from, is entirely broken. If you are familiar with how weaving is done, it's an inherently serial process. So my wife happens to have her own loom. There's a shuttle that runs backwards and forwards interleaving a thread across the warp. It's a serial process. The thread tracks across the warp and back. So it's a stupid analogy in the first place because it's completely wrong. It's serial. On the chip, each of those, that thread would instantaneously lace across the whole warp, but it doesn't in reality, right? Stupid. Okay, so we've seen the architecture, and now we think about the actual programming model. And there's a little bit of a gap between the architecture and the programming model. The programming model is basically, it is up to you, the programmer, to decide how you're going to partition your work across these multiple cores and across the floating point units in those cores. So you have to identify work-independent blocks, or independent blocks of your work. The work block assigned to a core, so you're going to chunk up whatever you're doing into independent tasks. And it's going to be the same independent task in each block, the same set of instructions. The data can differ, but it's basically the same set of instructions. And the work done in one block really cannot impact or influence the work done in any other block of work. Right? So there's immediately, it's up to you as the programmer to identify that partition of work in your code. That's conceptually the hardest part when you're looking at a nasty 100,000 lines of code, is actually figuring out where is that partition, or looking at a new algorithm, figuring out how to do that partition. If you've got an atmospheric code, for instance, good luck. You've got to figure out how to do this. There are no magic fairies. The code fairies will not come and visit your code. They will not write the CUDA implementation for you that partitions up your work magically and allocate it to the cores magically. It's up to you to do it. Each core processes the work group or work block with a work group of threads. The work group is batch processed in subgroups of SIMD work items. Each work item is processed by a thread passing through a SIMD lane or an ALU. So it's up to us to figure out how do we actually express this in the CUDA environment. So I've got a piece of example code. This is the code that's going to run on the host, on your regular PC that's got a GPU attached to it, or your MacBook, which has got its own GPU. This is sort of a good prototype for every piece of code you'll ever write. You're going to allocate some, you're going to allocate some memory on the device using CUDA malloc. You pass it the address to a pointer. It'll populate that pointer with an address. That address is not a pointer in your host memory. It's a pointer to somewhere in the device memory. In fact, recently, it's a pointer into a unified virtual address space. But for high performance, you should never treat that as a regular pointer. This d_a, you should really, ideally, never access that direct or dereference that directly in the host code. You should always use the CUDA memcopy to move data backwards and forwards. So you should treat this thing as untouchable memory from the host perspective. Then you need to specify, in this case, some dimensions for an array of threads. We'll look at that in a little bit more detail in a bit. But that's specifying a multidimensional array of threads that's going to process your task. In this instance, I've said I want blocks of threads. B is 17. I've randomly chosen 17 as a bad example. So I'm going to have 17 threads in each block. I'm going to work on a vector. I'm going to populate that vector with some values. Okay, the vector is a length 3,789. Does that divide by 17? Do we have any math savants here? Anybody with a calculator? Okay, so what I'm going to do is I'm going to have a thread touch one value in that array. And I'm going to group those threads into blocks of 17 threads per block. So I'm going to have 17 blocks, 17 threads per block. I'm going to tile this array into groups of 17. Okay? So in order to get enough blocks to cover the whole length, I can just do that little bit of arithmetic. I could just divide the length of the array by the number of threads in the block, but then because it's integer arithmetic, I may be short a block because I might have to take care of the tail of the array. because it doesn't divide by 17. So I'll have just enough blocks in this case, because what I'm conceptually doing is partitioning a task, right? In this case, I'm putting entries into an array. I want enough threads in enough blocks so that every entry in the array can be populated by one thread. And then what you'll see is something really nasty. Non-standard C has crept in to the CUDA, NVIDIA's CUDA C extension, which requires that you use the NVIDIA C compiler or CUDA compiler in order to compile this code for your host. So you actually need to use the CUDA compiler NVCC from the CUDA SDK in order to compile this code. It's not vanilla C. It actually requires a special compiler. Okay? And what it'll do is it'll generate an intermediate piece of C which will call the CUDA driver API, or one of the deeper level APIs. It'll turn that C, fake CUDA C, into regular C. So what happens is that when you can see that thing with the chevrons, when you make that call to that kernel, it will return pretty quickly, because what happens is it just queues up that kernel, this function call, to run on the GPU. Then we're basically just inserting it into a queue, and then you'll get control back on the host before it's guaranteed that that kernel is completed. So it's basically a non-blocking call to a function, and the function is executed on the GPU. Meanwhile, since we're on the host, we've got an independent processor. We'll allocate some memory for the result on the host. Then we use CUDA memcopy to copy a certain number of bytes back from that device array to the host array. That CUDA memcopy is a blocking call. It will not start moving data from the device to the host until the device has executed all of the kernels that precede that CUDA memcopy call. And finally, and CUDA memcopy is self-blocking because it will not return until the data is copied back. So after the CUDA memcopy, we're confident we have the data retrieved from the device. So let's look at that just process briefly. Allocate space on the device. Set up a number of threads you want to process that, number of threads you're going to invoke. Call the kernel with that array of threads. Allocate some space on the host, copy the data back from the device to the host. So there we go. Redundantly redundant. Okay? Yes?
Typically, we don't need to free it.
Oh, I was just being lazy. Yeah, there's a CUDA, it's either free or CUDA free or CUDA destroy. I can't remember which one it is. I always forget to do that. But that's bad news. So if you start leaking memory on the GPU, you'll run out of memory pretty quickly. So it is good housekeeping to call the CUDA free or CUDA destroy, whichever it is. Yes?
What if I want to use the CUDA main copy to copy some data that is not the DA?
Go ahead.
So you say it's the blocking call.
It's going to block until all kernels have completed before that. There is an asynchronous CUDA memcopy asynchronous, which will allow you to do that while kernels are executing. But that's more advanced. Okay. Right, so let's talk about the kernel language. That's sort of the basics of how you interact with the device from the host. But now we have to actually write that function that's going to execute on the device, right? The device kernel. But I want to motivate, so if I just give you the CUDA kernel language straight up, it's mystifying. So I want to motivate it by transmuting a serial function into a CUDA kernel. Okay? So in a serial function, this is what I'm going to do with that array. I'm going to take each entry in the array and fill it with the index value of that array entry. Okay? Pretty simple, a for loop, right? Okay. But we have to think about the structure of the architecture of the core, right? If you think about, we have 16 cores. Each core has multiple floating point units per core, right? So we have to identify how to divide up this task, which is basically loop partitioning. How do we partition this loop so that we have independent tasks for each block of threads and independent tasks for each thread in the block? So the simplest obvious way to do it is to partition the index space up into groups. And here I've called it batch 0, batch 1, batch 2, batch 3, or batch 4, block 0, block 1, and so on. Okay? So I'm imposing a parallel partition of my work. So if I was to do that, I would take that single for loop and make it a double loop. So we're going to loop over entries in the block and then loop over blocks. Does that make sense? Is anybody puzzled by this? It's pretty straightforward, right? It's implicitly what we're doing at OpenMP. We're actually partitioning a loop into a double loop, say. Now, has anyone noticed anything really odd about these for loops? What about the loop bounds? Where are they defined? Or put it another way, is this correct code? Not really, because nowhere have we defined the loop bound, the grid dim, the block dim. The block dim is the size of the block, how many entries there are in the block. The grid dim is how many blocks are there. That's got to be defined somewhere, so we're going to assume it's defined outside of this kernel, outside of this function. So we're going to assume above this says int grid dim is blah, block dim is blah. Okay? We'll come back to that in a little bit. And then inside the block, we take the thread index, the T index, the inner index, and the outer index, and we construct the index into the array, right? So this is analogous to taking an MPI rank, in this case, a multidimensional MPI rank, and constructing a single linear indexing from the rank. Does that make sense? Yes.
Okay, is that still it is still serial code?
This is still serial code. I'll tell you when we get to the exciting part. You wake up and there is CUDA code will just magically appear out of this. Okay. It says it even says in the title, tiled serial simple kernel, right? Okay. But this is the way that you can think about mechanically turning serial code into CUDA code. This is a very easy example. I've rigged this because the payload, the body of the for loop, every iteration is independent. But you might have some inter-iteration dependence, a loop carried dependence that can make this process much trickier. But for a simple problem like this, where you have each iteration of the loop being independent, you can do this loop partitioning without any issues, right? Notice, though, I've had to insert an if statement. Why have I had to insert an if statement?
It's not a multiple.
Yeah, it's not a multiple. So if you've had to allocate more iterations because the inner loop index, the block dim, doesn't divide neatly into the length of the array, you've got a tail, you've got a handle. So there's going to be some iteration at the end of the iteration space which shouldn't be doing anything. That's terrible, right? That's the worst possible C code you can write, because you've now introduced a conditional at every iteration. So we go from this rather simple serial code. We've had to introduce double nested loops with some magical loop bounds that get provided somewhere. But we're getting closer to CUDA because now the loop bounds are actually multidimensional. So instead of just allowing you to partition one for loop, you can partition multiple for loops, and you can have three-way nested for loops that each of those get partitioned. Okay? And the way that that's handled is by these multi-dimensional loop counters. So we'll have a .x, a .y, and a .z. So you could have 3 loops over blocks and 3 loops over threads. But we're just going to stay right at the moment just with 1 outer block loop and 1 inner thread loop. Okay? Does that make sense? So you've still got magically provided. Also notice that those block indexes, they magically appear out of nowhere. We're going to assume they're defined outside this function. So it's still serial code. Now what CUDA does in the way that you form the kernel is, because we have a multidimensional array of threads gets generated when we queue and the kernel gets executed, we don't need those for loops, because the for loop is implicitly constructed by having that many threads. Okay? So in this case, you'd have griddim.x blocks of threads and threaddim.x number of threads in each block. Okay? So each of those threads will have an index. It will be able to figure out which thread it is and which block it is. And all we need to do in CUDA, provide the inner body of the loop. Okay? So we went from a serial code with 1 for loop. We were able to partition that for loop by having a double nested for loop, which is nest over blocks, nest over threads, or thread and index space. And then the only thing that CUDA needs you to do is provide the work that each thread needs to do, which is the payload, the body of the inner thread loop. Yes?
One very stupid question. Actually, I want to know, block ID is a default global variable or something. You don't define it, just use it.
And this is a fundamental conceptual issue with CUDA, which is magically the thread knows its index. So that's an intrinsic variable provided by the CUDA framework. Every thread knows its thread index, its block dimension, and its block index. And those are 3-dimensional numbers. You can know it if it's in a 3-dimensional block of threads, and it can be in a 3-dimensional grid of blocks. In this case, we've only used the first dimension. That's an excellent question. Has anybody got a stupid question? Ah.
So what happens when you manipulate data, like several variables?
Fine. So let's be clear about what's happening inside this kernel. Every thread has its own variable space. Right? It has its own appointed registers. So each thread here will have an integer index n. Each thread has access to its own thread index, block dimension. Each thread will compute that linear index n for itself. Each thread will check to see if that's bounded by capital N. Each thread will have a copy or a register dedicated to that value n. Each thread will have a pointer into or have the DA pointer. And the DA pointer points to shared memory, which is, so this DA points to an array, start of an array in the RAM chips on the device. And all threads have access to all entries in that device memory. Okay? So the DA pointer, which was returned by CUDA malloc, is a pointer into a shared memory space. Okay? But obviously, they each have a copy of that pointer. Yes?
So you're saying we should just define this thread ID, X, and block dimension somewhere in the...
That's defined for us. It's provided by CUDA. So it's an intrinsic variable. It's like pi.
So
how do we control the number of threads? Or
Right, that's a good question. So up at the top, you see that when we called the kernel, we have that chevrons. The first entry is the number of blocks of threads. The second entry is the number of threads in a block. So that will define block dim.x and grid dim.x.
then they will automatically figure out their own IDs.
Each of them is created with that information. Okay? Yes?
Probably I missed the point, but so the dimension of the block and the thread, how it relates to the the actual GPU?
Fantastic question. There's almost no relationship. There are some limits on how many threads you can have in a block, which is limited at 1024 currently. There's a limit to the number of blocks. I don't remember what the current number is. Okay? But if you think about it, 1024 threads in a block, that exceeds the number of floating point units on a core. So what happens is that the threads in the block get partitioned into groups which match the size of the SIMD array. So they'll get chunked into groups of 32, and those will be processed independently. So you'll take, if you say I want 64 threads in a block, B equals 64, then those 64 threads will be created as will be processed in 2 sweeps through the SIMD units. Okay? So we don't have to exactly match the number of floating point units in a GPU core, but the caveat here is you want to avoid having 70 or 33 threads in a block, because that will take 2 passes through the SIMD units. 32 will be fully populated, and then there'll be 1 which goes through on its own. Right? So if you think about 1 thread going through a 32-lane highway, that's a bit of a waste. That's the Houston style of using resources. Okay. Any more questions? These are excellent questions. Yes?
Is there a way to work around this if statement? Because what we actually want is that like all the threads with number higher than n do nothing. But now, like every thread has to do twice the work because every thread has to evaluate this if statement.
Yeah. So there is an obvious solution. Can anyone suggest a solution?
Make sure it's divisible.
Right. Make sure it's divisible. So what do you have to do with that array? Pad it. Right? So you could just pad that array. Of course, that may be non-trivial if there's some indices that are part of this work task, that you'd have to make sure all indices are valid. So if you have indirect addressing, you have to make sure that you're going to be doing indirect addressing which is valid. But typically, if you want to get good performance, avoid conditionals, you can do it. Not always, but you typically can. So, yes?
So the three-dimensionality of dim grid and dim block is
Yeah.
purely just to help the programmer, right? That doesn't actually correspond to how the cores are arranged on the chip.
It goes back to the graphics world, where you really wanted multidimensional indices to get your location in the picture without doing modular arithmetic. You could have essentially achieved the same thing with bit masking and rotations, but it's just a convenience. It actually turns out to be very useful to have a multidimensional index. It just avoids some division. And excellent questions. This is really good. Anybody else? Yes.
I don't. Okay, it's not maybe not clear to me. How can you have a recursive loop? I mean, recursive function. Let's say you call a simple kernel or another function inside this. How does that work?
Right. So there are different types of functions. There's a device function, which will be executed by every thread that calls the device function, and that's basically just almost at the level of insert that function code, inline it into the kernel code.
So if I want to write some other function, can I call that from the kernel?
Yeah. So you would just have to designate it a device function, not a kernel function. So there's some other things that sort of are interesting that there's some extra syntax I threw in there without highlighting. If you look at just before the void simple kernel, we've had to designate this as a kernel. If we don't designate it as a kernel with underscore, underscore, global, underscore, underscore, they love underscores, these guys. Everything is underscored. If you don't have that, we can treat it, you could say, I think, underscore, underscore, device, underscore, underscore, and it will be just a function that can be called from within a kernel. There is some facility in CUDA for a kernel to spawn another parallel work task. But I think it can only be done at a block level. So you can do some recursive launching of kernels, and CUDA guy would know about this, but I'm not sure this is entirely encouraged. It's fairly straightforward to thread bomb your GPU.
Yeah, it's only supported on Kepler, starting with Kepler architecture first. Yes, we call it dynamic parallelism, so you can call kernels within kernels. So, and you can have like a single thread, for example, if you have a condition like a thread index equals 0, then launch a kernel, right? So then it will create like a new kernel will be launched, so the whole new grid will be launched on the GPU.
But you have to proceed with caution because...
Yeah, you have to proceed with caution because if you have some data dependency, for example, you need to insert the synchronization of this kernel because, the kernel will be started, right? But then, of course, you have to kind of synchronize and then it kind of gets tricky. So it's useful in case we have like a data that spawns a lot of other data, that spawns a lot of other data, right? So kind of hierarchical thing. So this is where the dynamic parallelism can be useful.
But I've avoided it at all costs because it's prone to issues of programmability and correctness. It's very difficult to make sure you do it right. Okay, so the novel piece of syntax is that you have to say it's a kernel, and you're using basically the thread rank to figure out which thread should do what. I've imposed my bias to use a linear reconstruction of the thread indices, but I could have obviously done something much more exotic and decided, based on the thread index, so it's some nonlinear decision, what each thread would do. But no need for that here. So I have some examples here for CUDA, but you have very limited access. And just to go through the simple setup, you would compile this. It's not a .c file, it's a .cu file because it's a C extension, C++ extension, and you would compile it with the NVIDIA CUDA compiler, but you would run it as a normal piece of code. Okay. So let's just go to look at a slightly meatier example. We're going to use the Poisson problem, two-dimensional Poisson problem. So we're going to think about how we're going to set up the system, linear system we want to solve for the Poisson problem. We're going to, first of all, discretize, take those second-order partials and replace them with central difference formula. And we're going to look at the solution assumed to be collocated at nodes in a grid. Okay, so they're doubly indexed nodes in a grid. And this is going to be where getting hold of thread indices in multidimensional thread indexing turns out to be very useful because we can locate ourselves in a two-dimensional array of nodes just using multidimensional thread and block indexing. So if we look at how the data dependencies, the thread at this ij node is going to depend on the 4 neighbor nodes. Sorry, not the thread, the value of the solution at this red node depends on this, the values around it, and collectively there's this global interconnected dependence. So what we're going to do is solve this with a simple Jacobi iteration, where we're going to iterate towards a solution, and we're going to use a standard stationary iterative technique, and we're going to bully that around into, oh, finally I've got a pointer, into this update sequence. So given an initial guess, we will iterate of k equals 0. We'll just assume everything's 0. So we'll just change the values of the node based on the forcing, the right-hand side force function. And then we'll iterate this formula, increasing k over time, or over iterations. And we're going to have a termination criterion, which is basically an L2 termination criterion. Right. Does the solution change a small amount over each iteration? So we'll map that onto the GPU. So if we're going to work in serial code, it would be pretty damn straightforward to just do one single iteration. The new value of the solution is a quarter of the right-hand side plus basically the average of the node values around each node. Right? Would anyone like to comment on this? What nice properties does this Jacobi update formula have? Are there any loop carry dependencies? Right, you update a value in a new array based on values in an old array. And they're all independent update formulas, right? So it's screaming embarrassingly parallel, right? There's no loop carry dependence. There's no number accumulating over the iterations. It's just new values depend on old values. So we can partition this array pretty much any way we want to. Partition these loops pretty much any way we want to. Yeah.
When you say embarrassingly parallel, you're referring to embarrassingly parallel in a shared memory environment, right?
Correct. Yeah, absolutely. If we had independent memory per floating point unit and they only knew their local values, then we'd have a problem. But they're able to communicate through the shared memory. Excellent point. Okay. So just to do a quick flipperoo, we're going to partition the I loop into blocks in I and threads for each block. We're going to partition the J loop into blocks. So what we're really doing is we're chunking up this two-dimensional array of nodes into little squares. Each square will be handled by a core, and there'll be more squares of nodes than there are cores. So there's a task manager on a GPU which will keep just creating blocks of threads and allocating them to the cores until all the blocks that have to be processed are exhausted. Okay? So just as we did with the one-dimensional array modification, we'll do the same thing, but now we just have to do two things. We have to reconstruct our linear index, so we're going to create a two-dimensional block of threads and a two-dimensional grid of blocks. And then from our block indices and our thread indices, we're going to construct the coordinates in the two-dimensional Cartesian array. Okay? So we've got rid of those double for loops, and we've got now an I index, which is reconstructed from the x coordinates of the block, the x coordinates of the thread, the j index, which is constructed from the y coordinates of the thread in the block and the y coordinates of the block in the grid. Now we have to check two things, because remember, the blocks may not exactly tile the grid, so we have to make sure that these are valid indices. And once we've done that, we're good to go, because then we can just do that update. So that's, again, just a slightly more complicated version of the simple 1D example we have. We now have a 2D partition of the work. Everybody get that? Those serial for loops are replaced by implicit parallel for loops, which are handled by an array of threads, in this case, two-dimensional array of threads. That's the easy part. The harder part is, how do we figure out if we should stop iterating? We have that termination criterion. We have to check, did the solution not change very much? So we have to compute the L2, discrete L2 norm of the difference between the solution now and the previous solution. But if we look at that, that's basically, we'll simplify that L2 norm into just summing up values. Now that's bad. Why is that bad? It's reduction. Why is reduction bad?
Everybody involved.
Each iteration depends on all the previous iterations if you're going to turn this into a for loop. So it has a loop carry dependence. So what's the solution? Sorry?
Pass it to CPU.
Pass it to CPU. No, because that means you're shipping all the data onto the CPU at a bandwidth rate of 12 gigabytes per second, whereas the data on the chip is running at 300 or 500 gigabytes per second. So you've introduced a serial bottleneck, which is quite serious, or at least a data movement bottleneck, which is serious. Do we have any better improvements? Yes?
Just share the
What's that?
Just share the data.
Share the data? It's already shared. It's in device memory. It's available to everybody.
Tree-wise reduction?
Tree-wise reduction, correct. That's one way to do it. Yes?
Use shuffle.
Oh, too fancy. Well, that would be the thing I'm not going to tell you about today. But yeah, someone has done too much CUDA here to be in this session. Right. So first thing is we want to break that sum into nested sums so that at least we'll have a sum that can be done in a block. Right? We always have to look for that ability to partition for loops. Right? Think of the sum as a for loop. Okay? So the good news is that each of these partial sums of the reduction can be done independently. They don't depend on each other, right? So at least we've got a good block partition. What we'll do is we won't sum up those block values directly. We will just partially reduce the vector from a long vector to a shorter vector. Each block will output a partially reduced, or take a block of data, partially reduce it to one value. Okay? If we do that enough, we can reduce it down to the point where we can ship the data to the CPU, or we can just keep doing this partial reduction until we got one value left. Okay? So we do exactly what we do in MPI, which is a tree-wise reduction. So this is pseudocode for what a thread should do. It should find out which thread it is. All the threads in the thread block should be alive when we start. Then what we're going to use is something we haven't discussed yet, which is that well, we've mentioned it, but we didn't dwell on it. Each core has a pool of shared memory, a scratch pad, which all threads executing on that core can access, or each threads in the thread block can access. So what we'll do is we'll prefetch part of the vector into shared memory, and then we'll use that shared memory to do a successive reduction of the data down to one value for the block. So in this instance, I've got 8 threads. They're going to load 8 values into shared memory. Then I'm going to kill 4 of those threads with an if statement. Then when we've got 4 threads alive, they're going to add up 2 values each and put the result into shared memory. Then I'm going to kill 2 of those threads. Then we've got 2 threads left. They'll do part of reduction. They'll do 2 adds, an add each. And then we'll kill 1 of the threads, and we've got the answer once we've done that final add. Okay? So we're going to progressively lose parallelism. But in this case, this is a highly memory-bound problem. So most of the work is actually, most of the time consumed is in moving data. It's not actually in the work being done with that data. Once the data is in shared memory, as long as you access shared memory in a safe way, then this is all highly parallel. It's relatively fast compared to the actual data movement time. So basically, we can just execute a while loop, or we can unroll the while loop if we know how many threads we have in a thread block. Every iteration of this while loop will just kill half the threads, and we'll keep iterating until we're done. Then each thread block, we'll choose one thread to arbitrarily write out the partial reduced vector. Okay? But it does need some synchronization. Although you might think of all threads executing each statement in lockstep, that's not actually how it happens, because remember, we're batching the threads into groups of 32. So we have to make sure that everything is synchronized in the sense of when we write to shared memory from the first time, we have to make sure all threads have written to shared memory. So we need to introduce a barrier to make sure that the writes to shared memory have been done, and it's a good time to actually read stuff from shared memory. So this is what the CUDA code would look like, or simple CUDA code to do this. You allocate some shared memory, which is a resource available to all threads in the thread block, just with underscore, underscore, shared, underscore, underscore. We'll figure out which thread we are. We'll, if I'm a valid thread, I'm going to load data into shared memory. Then I'm going to designate the number of threads alive as the number of threads in the block. While the number of threads is greater than one, alive threads is greater than 1, we'll synchronize to make sure shared memory is available and been written to. Then half the threads will be killed. The remaining half will do the sum reduction, we'll just add 2 values, write it into shared memory, and then we'll keep looping around, synchronizing, adding, synchronizing, adding, well, synchronizing, killing, adding, and keep repeating until we're done with the reduction. Okay? And that's an example of how to use shared memory. That's the way I'm introducing shared memory through this example. It's a collective scratchpad array space that you can use in all threads in the thread block. Yes?
So how do you determine whether something is memory bandwidth bound or not?
Back of the envelope, look at number of operations you have to do versus...
Is it by paper, by inspection?
That's one way to do it, yes. Yeah. Usually you know what you're trying to do. Yeah. In practice, when you actually, if you've got everything right, you'll hit some roof line of performance, and it usually corresponds to data movement is the dominant cost, or floating point operations. If you're doing a Mandelbrot, for instance, with thousands of iterations, then you might be able to generate enough floating point unit work for that to be the dominant cost. But you actually have to inspect, you have to understand what you're doing. Yes?
The sync thread call can only synchronize the thread within one block, right?
Excellent. That's a fantastic point, and I wish I'd made it myself. Sync threads is purely a synchronization point for threads in the thread block. If you've got B threads, all B threads have to get to the sync thread and enter the sync thread before any of the B threads can exit. But it's only synchronizing threads in that block. It's not a global synchronization. In fact, it's extremely dangerous to try and achieve global synchronization of threads in the thread grid, or threads between thread blocks. Because if you think about it, if you weren't careful, you'd run into a situation where threads that have not been launched yet have to be involved in the synchronization, so you can deadlock a machine if you really try and go for global synchronization. So the best available, there are 2 types of synchronization here. You can synchronize threads, and you can synchronize between kernel calls. So there's a local block synchronization, and there's a synchronization between kernel 1 and kernel 2. So you can globally synchronize by exiting a kernel. Every thread exits the kernel, then before the next kernel gets executed. Does that answer your question? Excellent.
And how does the code look like if I would like to use the cache property?
Well, that's a cache, that's shared memory. That's a user-managed cache.
Sounds like a scratch pad.
This is a scratch pad. You're managing coherence. Right. Through that synchronization, you're managing coherence. Okay. And there's examples and some possible things you could, if you really want to get into CUDA, you can go and work through this list of things to do. Okay, kind of short on time, so there's lots of funny quotes, you can go read those. But I just want to talk about some of the things you have to pay attention to when trying to write optimal code. The one crushing thing is the NUMA structure. Register latency is single digits. Shared memory, and this is actually out of date. Shared memory has a higher latency. global memory latency is on the order of maybe 1,000 cycles. There are various cache systems which can have a range of latencies, but may be able to reduce traffic across the bus between the device and the device memory. So you really have to be quite careful about the amount of data you're shipping around. The rule of thumb I have is if you load something from device memory, you should do as much as physically possible with that piece of data before you write out data to device memory again. And you should be particularly careful about how much data you're going to move between the device and the host, because that's a serious bottleneck. Let's see. There are some other gotchas. If you think about this array of threads, all the threads in a thread block have to be resident on the core. If you think about it, they're context switching between the different SIMD groups and then between different thread blocks. And the minimum requirement is the thread block has to be resident on the core. So if you think about the blocks, the threads in the block, each thread consumes resources. It consumes register variables. It consumes shared memory. So if you want to write code that takes 1,000 registers per thread, you're going to quickly limit the number of threads you can have in the thread block, because there's a physical number of registers available, and they all have to be available to the thread block. So you already start to think that means that you can't necessarily just take your piece of code you've got now, which is a Fortran vomit of code with thousands of registers declared in each function, because you've quickly exhausted the amount of register space, especially if you want to have a large array of threads. So a rule of thumb is you want to have a small number of threads, a small number of registers, 10 registers, 20 registers, 30 registers per thread. A register you can think of as an integer value or a floating point value variable, right? You don't want to have a huge number. You don't want to have a thread that requires a large stack array, for instance. It just will not fly, because that's going to consume registers. If you consume too many registers, it will spill into the device memory, and that will involve that high latency. Okay? So it's not necessarily a straightforward process to go from existing legacy code to CUDA code, because you're typically are constrained by number of threads that you are available to each register. You also have to be careful with that shared memory. The shared memory is parallel memory in itself. There are multiple banks of memory which are interleaved, and you have to be careful to make sure that you don't have threads oversubscribing each bank in the set of banks of shared memory. It's funny when you talk to guys who used to program Cray machines, they're very familiar with memory bank conflicts. You're not so familiar necessarily with when you're programming Intel devices or Intel CPUs. It's not really paramount in your memory, but the way you work. But you have to be careful to make sure that, so if you've got a shared memory array which is running vertically across the banks, the first entry in shared memory would be in bank 0, the second would be in bank 1, bank 2, and bank 3. You have to be careful you don't have all the threads accessing the same bank. So in this case, we have sequential entries in the shared memory being accessed by sequential threads. That's fine. There are 32 independent banks being served by 32 independent memory managers. That's fine. You can even mix it up. They don't have to be sequentially aligned, as long as there's a one-to-one ratio in bank to access. But if all threads, in this case it's okay because it's a broadcast, all threads can receive entries from one bank. But if you have all threads accessing the same bank, then we have a problem. So there are some hidden gotchas to using the scratch pad. You have to be careful that you don't run into some hidden traps. It's also the same, if you recall at the beginning I started talking about partition camping. It's the same thing but at a small scale. So partition camping is where you have all the threads trying to access just memory that's in one of the physical RAM chips, not distributed across multiple RAM chips. Okay. That's too detailed, and it turns out that the difference between CPU and GPU is not that stark anymore. On the CPU, you want to use unitary strides and maximize cache access. You want to use unitary strides and page-aligned access, memory access. If you want to fully use the cache system, same on the GPU, where you want to access sequential memory addresses for best performance. Vectorization also forces you into page-aligned memory access. And on the GPU, you want to avoid conditionals, but you also want to avoid conditionals on the CPU to maximize SIMD vectorization. And if you're going to look at the level of OpenMP threads or thread, you want to make sure those are independent as possible. And it's similar on the GPU, where you want to make sure that there's no interference between work in distributed at different work groups. So they really aren't that different. Okay. Next topic. Have we got the energy to get to the next topic? Right. We've covered CUDA. We've got the sense of what it is. We know the architecture. We know the kernel language. And we know the host API. That's the mechanics of how do you interact with the GPU, how you move data, how you work on that data. Okay? OpenCL. It's CUDA, but not. It's kind of the same thing, but it isn't. Mostly it's the same thing. CUDA comes along in 2007. It's basically the outcome of some PhD theses at Stanford. The really good people from Stanford went to NVIDIA, and out of that came the CUDA framework. There was maybe a less successful a version of this that came out of AMD. So AMD created something called Brook Plus, Brook Stream, CTM, and variants. And they weren't nearly as popular. But CUDA somehow stuck. NVIDIA is very good at marketing and getting community together and building up around their products. So Apple paid attention to this very quickly and said, oh, that's interesting. We want to build support into OS X for this type of general purpose accelerated computing. But they didn't want to be solely dependent on NVIDIA for GPUs, because that would obviously push the price up and would also be a single point of failure, which would be an issue. So they brought together a number of manufacturers and created a standard under the Kronos group. And you can go to kronos.org, is it? Yeah, kronos.org/OpenCL. And this is an open standard variant of CUDA. I think I've got a timeline. Yeah, so you've got Apple somehow, by its position in the marketplace, managed to get mortal enemies, AMD and NVIDIA, to participate in a common standard. How they did this, I'm not sure, but they somehow managed to get this to work. And a bunch of other people, but that's the main, the main contributors. So Apple had a slightly bigger vision of where this could go than NVIDIA. They wanted this unified framework which you could use CUDA-like programming models, not just on the GPU, but also on the CPU, or on a field programmable gate array, on embedded devices. They wanted it to be a ubiquitous way to program many-core, multi-core devices. So the timeline, so you have the work at Stanford, it's Brook GPU. Best guys go to NVIDIA. NVIDIA releases this in 2007. So you could do some of the CUDA-like stuff in Brook. It was much harder to use than CUDA. CUDA made it relatively easy to program these GPUs. You've seen it. In just like an hour, we've actually covered the mechanics of how you write CUDA code. 2008, AMD responds with the Stream SDK, which is their Brook Stream. You know, you can see the lineage of these APIs. But CUDA gets momentum. Apple notices 2008, May 2008, they propose an OpenCL working group. October 2008, Kronos produces the standard. Between 2007 and 2008, how does a committee create a new standard? How does that happen? Suggestions? How do you do that? How do you spin up a whole new standard?
Push your agenda.
Take the most reasonable parts of existing stuff, mash it together.
Steal. Right? They basically take CUDA, which has some fantastic ideas buried in there, and make it generic. Right? And we'll see how shameless this is. I'll show you in a second. So, you're basically designing a programming environment, a kernel programming language, and a host API. So what does that involve? Well, you need terminology. A kernel in CUDA becomes a kernel in OpenCL. A host program thread becomes a work item. It kind of divorces it from that notion of a GPU thread into a slightly more generic piece of work that gets done. Thread block becomes a work group. Grid becomes an n-dimensional range. ND range is an index space. Okay, so remember how we could find out the thread rank and the block rank? Well, they tidied that up. They did a better job. Instead of having these nebulous intrinsic variables that each thread happens to know, it becomes a function call, which is really just a macro, which produces the thread index. Get local ID. So usually I ask people, so hands up if you prefer the CUDA version from the magic thread index variables or the OpenCL version. Who prefers CUDA? Who prefers OpenCL? It's much less ad hoc, right? You actually got an interface, you can query the interface, and it tells you what your thread index is. You can get your global index. You don't even have to dick around with the block index, thread index. You can just get a global index for you. It's something that happens over and over again. When you write kernels, you're using that same piece of code over and over again. It might as well be a macro. Grid dimension, you can get number of groups. Block index, get group index. Block dim, get local size. Grid dim times that's the total number of threads, get global size. So they tidied that up. Good for them. That's actually an improvement. They got rid of some of the underscores, not all of them. Global becomes kernel. Device function just becomes function. Constant variable becomes constant. Device becomes global. So, and unfortunately, in CUDA, shared memory becomes local memory in OpenCL, which is unfortunate because in CUDA, local memory means something else. But if you just forget CUDA and just pay attention to OpenCL, you'll be okay. The memory model is, of course, the same because the architecture is the same. Because we want to use OpenCL to program these NUMA devices. There's local shared memory, there's register memory, there's various levels of cache, and then there's global device shared memory. So the diagrams don't change. This is pretty generic across these multi-core devices. So the kernel language, I think, improved. You write kernels just as you did before, but you just do that grammar replacement, or you just do the word replacement, string replacement. The host code gets more complicated, and this is where the committee field comes in, because you have all these manufacturers. And if you think about a PC, the PC might have an AMD GPU, it might also have an NVIDIA GPU, it might have Intel CPU, and it might have several other things buried in there. So you need to be able to selectively choose which device you want to compute on. But it's even more redundant than that because each device might be supported by multiple different implementations of OpenCL. So you have this problem of a combinatory explosion of devices and platforms, which is the platform is just fancy word for implementation of OpenCL. So you have to choose get a list of the platforms, get a list of devices on the platforms. Then you need to actually create a context, which is your way of interacting with that device on that platform. Then, because you're going to create multiple queues, you're going to create a queue on that device on that platform. This becomes a sing-song sequence of things you have to do just to get started. So in CUDA, well, you're going to include the CUDA.h in OpenCL, Apple is just difficult, so they have a different place that they put those OpenCL headers than the rest of the world. In Linux, you'd use CL/. In CUDA, you don't have to do anything special to get a device because there's a default device. In OpenCL, there really is no, well, it might become a default device, but typically you have to figure out which platform, that's which manufacturer's OpenCL. You have to choose a list, get a list of devices on that platform, because there might be multiple devices. So you have to choose a device. Still not having to do anything in CUDA, but in OpenCL, if you're going to work at this level, you have to create a context, which is your way of interacting with the device. Then, optionally in CUDA, you can create a queue, or multiple queues, but or what they call streams. OpenCL, you actually are obliged to create a queue, which you're going to put in your kernel requests into that queue. Oh boy. So that's how we've just got to the point where we've got a queue we can push commands into on the device. But that's not it, because now we have to take our code and inject our code, or set up our code so that we can run it on that device, on that platform, on that queue, on that platform, and so on. So because you're not always guaranteed to have a certain type of device at runtime. What typically happens is people will compile code at runtime. So we'll actually build the code, the kernel code, when we're running, because we know at that point what the device is and what platform and so on. So we have to do that online. So we're going to create a program with source, build the program, look for compiler errors, because of course the code might be wrong at compile time, and then we're going to create a kernel from that program. Whew. So we're going to create program with source, build program, create kernel. So we've got we've now built a kernel that we can execute on that queue that we created. Okay, but that's not the end of it, because now we have to go about creating the buffers. That's the equivalent of CUDA malloc, where we're actually going to store data on the device. But then it gets really messy, because a kernel is not strictly a callable function. So we actually have to pass it the kernel arguments one by one with CL set kernel arg. So if you think about a function call, you would just call a function, you give it a list of arguments. But now we actually have to manually feed those arguments into the kernel when we want to call it. Then specify the local workgroup size and group threads just like we did, but we actually have to make function calls. We're not going to use chevrons because the OpenCL API is a regular C API. It is not a mangled version, or not an extension of C. It's a regular C. So we're going to treat OpenCL purely as a library that we can interact with. That's a positive check. We like that. Okay? We don't have to mess around with MVCC and interoperability issues. Are we done? No, well, then we have to queue up the kernel, and that's another API call, and then we want to wait for the kernel to finish. We'll call CL finish. So in CUDA, you'd use CUDA malloc. In OpenCL, you'd use create buffer. In CUDA, you specify the size of the grid of threads and just call it. In OpenCL, we have to set the kernel arguments, then specify the number of threads, and pass all of this into the ND range kernel call. Are we done? Well, then we have to write the kernel. Well, the kernel's easy. Remember, OpenCL stole kernel from CUDA. So you can see we just had to change global to kernel and the thread index to global ID. Okay? That's the easy part. And I've uploaded an example to the GitHub, so you can actually see the example in toto. This is just to take an array and fill it with the array index values. Get the platform, get the device, set the device, get the context, get the queue, take the text for the kernel, create the program with the source, build the program, get the program build info, make sure there wasn't a compile error, create the kernel, create the buffers, set the arguments, and call the kernel, finish, and read the data back. That is why OpenCL wasn't initially very popular. because just going through each of those steps seems like just a pain in the ass, if I was to be honest, and it is. However, you have to balance this with the notion that the OpenCL is much more flexible than CUDA, because you can use OpenCL on pretty much anything. NVIDIA GPU, AMD GPU, Intel CPU, Intel integrated graphics, depending on the model, AMD CPU, and so on. I think even Intel's Phi accelerator. So, and even FPGA devices from, I think, Altera. IBM CPUs, IBM Blue Jeans, I think you can do it on that too. I'm not sure the level of support. So with that extra degree of choice comes this extra pain in the neck of having to actually set up the specific program for the specific device, and then the API is a bit clunkier than the original CUDA API. Okay, any questions about that? So, yes?
So all this additional work, you just have to do this once at the very beginning.
Yeah, it's trivial. And in fact, if you're a reasonable program, you'll just hide that behind a simplifying interface. You just, it's kind of like calling a Fortran legacy library, which takes 50 arguments. You hide that behind a decent front-end code. You really only have to do most of that once. You do have to do the data movement, so the read buffer, write buffer stuff would happen. But again, I would hide that behind an interface. Yes?
We have tried the same code on CUDA as well as OpenCL on the same graphics card, NVIDIA.
You could use OpenCL, or you could use CUDA. You don't have to do both.
We have a graphics card, and we have tried the same code with using CUDA and using OpenCL.
You choose.
And OpenCL performs pathetically as compared to CUDA.
I've got some comments about that later on. That's a complicated question. Yes?
If you have put a lot of effort in programming and in CUDA programming, and one day you have to port your program into something else, some architecture, I will not ask if there is a way to do it, but I want to ask you, what will you do?
Fantastic. That's the third part of this tutorial. The question was, basically, she doesn't want to have to keep reinventing the wheel every time one of these new threading languages comes out. How do we avoid that? The answer is abstraction. We create an abstract interface, and we hide all this nonsense of CUDA, OpenCL, OpenMP. We hide it behind the scenes. And we have a unified way of programming through to any of those. So in the end, we shouldn't address these threading models directly. It's important that you see how they operate, because then the abstraction will make sense.
It's just not to build the kernel at the runtime.
You can save the binary, but you'll need to load the binary, which is a slightly different CL API call. Okay. So slightly different from how you compile up a CUDA program. You're going to use your regular compiler, U++, Clang, whatever you're using. And then you'll link OpenCL as a library. You'll had to install an OpenCL platform or multiple OpenCL platforms. If you install NVIDIA's CUDA SDK, it comes with a platform. An OpenCL is buried in there. They stopped documenting it for a while. I think they may be documenting it again. In fact, NVIDIA said that they wouldn't be supporting OpenCL 1.2, but then they backtrack on that, so they are supporting 1.2. Right, so that's an example. And just to give you the sense of the side-by-side, the kernel language is pretty much the same. The thing that really varies between CUDA and OpenCL is the host API, the way you interact with the accelerator device. Okay, that's the thing that's different. But as sagely pointed out, you don't have to keep interacting with the OpenCL API directly. You should always sort of hide that behind the scenes so that the application developer doesn't really interact with it very much at all, and focus the work on developing the kernels. The reduction is the same. The one reason I put this in here is because instead of shared on the left, it becomes local on the right. Instead of having async threads, you'll use a barrier. There's a couple of different barriers in OpenCL. One is for the local memory fence, which makes sure that the thread's barrier until all reads writes to the local memory have been completed before exiting. It's a little more fine-grained than that sync threads barrier. I went through that pretty quickly because, one, you've got the slides, but secondly, because it really is just a sort of more generic version of CUDA. You've seen the principles in CUDA, which I lingered on. OpenCL is basically like a portable CUDA, right? So in this part, I want to do sales for my thing, right? This is what we're trying to do is avoid directly being exposed to precisely the issue that was raised at the back there. Exactly the point that was raised at the back, which is you put the effort into implementing code, you don't want to have to go back to it and re-implement it unless that's your job. If it's your job, you want to do that as many times as possible for job security. But if you're a physicist, you want to code once and forget, right? If you're the domain specialist, geophysicist, physicist, whatever, chemist, you don't want to have to revisit the code because that's not where the value is in your work. The code's just an expression that gets you to what you want to do, right? You're not in love with the code. You just want to code it once and forget it, right? So, as I said, I have all these people in my group, and we have this issue of I want to write codes that we want to be able to use in 20 years without having to go back and revisit them, right? I don't want to have to do that, right? I mean, it's bad enough looking at my code I wrote 2 months ago. I don't want to go back in 10 years and have to look at the code I wrote 10 years ago because the way I look at code changes over time, right? So this is what we developed as a partial response. The 4 primary candidates right now for programming these devices or programming many-core, multi-core devices are OpenMP, OpenACC, CUDA, and OpenCL. OpenMP, OpenACC are basically directive-based. We've seen OpenMP. You've had quite extended tutorials on that. You insert pragmas into the code to say this for loop should be made parallel, right? You create a schedule. You create a partition for that for loop. OpenACC is a bit more complicated because now you have 2 things to worry about. Not just the partition of work, but you have the issue of data location. If you think about a code, you've got data that resides on the device, data that resides on the accelerator. So OpenACC differs from OpenMP in the sense of you have to actually push data around and say, this is data on the device, and we really need to move it onto the host. So it's really not as clean as OpenMP. OpenMP is actually fairly straightforward because it's the right type of idea. It says, divide this work up. But OpenACC, you have to say, divide this work up and move this data. So you have different types of directives that will lurk in different parts of the code. And keeping coherency of these directives, which are scattered now, is actually quite, in terms of robust development, is actually quite tricky. Because you have to have a global sense of the code to make sure that at some point in the code you, in a timely fashion, move data to the device, and then when you partition the work, it's working on data that's already on the device. If you're really looking for performance, if you're not really looking for performance, then OpenACC is probably a good option. But then you have to ask yourself, why are you even bothering with accelerators in the first place if you don't care about performance? So CUDA, in the original version of CUDA, it's very much up to you to move data around, but it was done by API. So it's a little bit easier to keep coherency when you have an API you are explicitly interacting with and you are guaranteed that what you try to do either happens or you get an error code. With directives, these are suggestions. With interacting with an API, you are literally saying, do this, right? There is a subtle difference there, and you have to be careful about that. But it's proprietary. So OpenCL is the more generic, standard-based version of CUDA. But as you've seen, it has its own levels of extra complexity because now you have to manage potential for multiple devices, but again, you aren't locked into a single vendor. So we're now faced with this issue of MPI plus X. What does X equal, right? MPI plus X could be MPI. Some people like this idea of MPI processes spawning MPI processes, and locally you'd have global MPI across nodes, and then inside a node, internode, you'd have MPI running MPI processes. Fine. Or you can go MPI OpenMP, MPI pthreads, MPI CUDA, OpenMC, whatever. But we don't know what X should be, really. And X may change depending on the architecture you're working on. Right. So we have this uncertainty about X. We don't know what X will be. We don't even know what it is right now, given any given machine that you're trying to run on. We don't know what we're going to be programming in a few decades. Architecture and API life cycles are measured in more doubling periods. So the problem is that architectures come and go. This is where I upset some people, and I say, has anybody programmed the cell? Oh, I'm in good shape. Sometimes I run into audience with several people who spent a lot of time tuning their codes for the cell architecture, which was used in the Roadrunner machine. Put a lot of effort into tuning up and writing good code that ran fast on that machine, which was the cell was discontinued. So, that's a problem, right? BlueGeneQ, how many of you are using that? How do we feel about our lives? Right. So you don't want to overinvest in any given architecture. But there are other issues about portability. So you have all these different competing programming models. None of them are really code compatible. You can't just take CUDA code and run it in OpenCL. There are some tools that translate between these different models, but if you add a translation step, that can bring in extra trouble. And as I pointed out with old Blinky, when my CUDA laptop died, I'm now obliged to use an AMD GPU. I mean, if I'd written just CUDA code, then I would be in trouble because this machine here, you can use OpenCL, but not CUDA. So you write your code in CUDA, say, and then you want to run on a Intel chip or on an AMD accelerator. You can't really do that, not robustly. So you might do a port where you port to OpenCL. So now you've got bifurcated code, but the OpenCL code doesn't necessarily get good performance on the CPU or on the NVIDIA GPU, so you might want an OpenMP implementation. So now you've got 3 implementations. You discover a bug in CUDA. Now you have to fix your OpenCL code and your OpenMP code and so on. So you've got this nightmare of a support. And there are industrial codes. I was actually, I may be a professor, but I spent a semester at a company. And they were faced with precisely this issue. And in fact, my graduate student was an intern at that company, and his job was to port from CUDA to OpenCL and OpenMP. He's a very smart guy, but he's basically doing string replacement and then chasing bugs around in this vicious loop. So my response was to create CUDA, Occa. That we're not the only people to be addressing this portability issue. There are multiple solutions. You have lab solutions, including Cocos and VexCL, which are sort of array classes on steroids. You have Raja, which is more heavily C++. You have us, we do various things, and then you have some progressively lower and lower level translators. But I'll try and explain what we do in Occa. So here's a dilemma we have. We have x86 chips, accelerators, GPUs from different vendors, and then you have this problem of choice. You might want to use OpenMP on the x86, You might want to use OpenCL on the AMD GPU. You might want to use CUDA on the NVIDIA GPU to get best performance. If you think about a manufacturer, they're going to invest in their own platform dedicated to their own device or best suited to their own device because they have limited resources, right? They're going to invest their effort where they're going to see the most return. So you probably really want a native solution for a given device. That's the sort of the reality here. OpenCL is cross-platform, but it's not necessarily optimal on every platform. That was a question that was buried in the question earlier. It's not necessarily, you can run OpenCL on everything, but it may not give you best performance. That's a generous assessment of the politics behind OpenCL. So what we did is we created an intermediate representation. That's basically a generic macro-based kernel language that, with the right definitions of the macros, would be valid OpenMP, valid OpenCL, and valid CUDA code for a kernel. Okay? So we could automatically generate functions that would run in the native mode on whatever hardware's at hand. But it was a bit heavy-handed because you had to really understand the macro language. So what we did is my graduate student, David Medina, created a parser which would take a more lateral C or Fortran kernel language and convert it into the intermediate representation, which would then run on whatever backend that you chose, on whatever hardware you're going to use. So what we've done is created sort of, what's a good word for this? Esperanto. Generic language, which is supposedly simpler than organically grown languages. Right, but since we had a parser, we also let you program the kernels in OpenCL or CUDA if you really want to do that to yourself. So you can either create a kernel in CUDA or OpenCL, or you can create it in a natural Fortran language or a natural C language, and then we'll just convert it into whatever backend you prefer. We have a research project, and this is very much, this isn't in production. The OKL, OFL, Fortran, and C kernel languages are in production. We have all our application codes, finite difference, finite volume, finite elements, spectral elements, algebraic multigrid, all sorts of different codes are built using OKL and OFL. We have a kernel language which is much more speculative, which is just regular serial language, which is our next step, where we're going to try and get to the point where we can take your crappy atmospheric code and automatically turn it into kernel code. But that's a work in progress. And then at the front end, we provide interfaces so you can interact naturally through C, C++, Java, Fortran 90, Python, and Julia. We had MATLAB, but nobody was using it, so we had to get rid of that because of just limited resources for support.
Why did you bother with the Java interface?
Good question. The student who developed this has gone into a company which uses Java. You know that there are Java interfaces to CUDA, JAR-CUDA, and Java interfaces to Python, PyCUDA, and so on. This just makes it generic across different front ends, back ends. Okay. There's a web page. It's actually quite a professional, nice-looking web page. There are lots of broken links, so don't look too deep. So we have portability. You can write in CUDA or OpenCL, or you can write in these more natural languages. But it's not necessarily guaranteed. It's probably unlikely that that code will run equally well over all these different backends, right? So we've created this unified approach, but it may still be the case that you have to implement specific kernels for specific architectures. Okay, so it's not a magic. It's not a panacea. It's not going to fix every problem known to programming kind. But the possibility is there. We try not to rag on the directive-based stuff too much, but the looming problem we see with OpenACC is maintainability. Because now the directive-based approach in ACC is going to force you to insert pragmas for copying data into the device, copying data out of the device, and directives for actually parallelizing the work. I think this is going to be challenging to keep coherency of the data movement and the data processing over large codes. OpenMP is okay because the directive tends to be localized. You take a chunk of code, you put directives around it. It's obvious what the directive is associated with. It's associated with parallelizing the work. But now in OpenACC, we have this extra load where you have to actually maintain the data movement. I think over time that will get better as data movement gets automated, but I think that's a problem. We're not the only people to do source-to-source translation. This actually happens in various different packages, but they've all either stopped being maintained or are several versions behind the current CUDA. There are several libraries. These are great. We can interact with the libraries. We can exchange raw pointers from CUDA and so on, but we're a little bit lower level than this sort of library-based approach. So what we've done is we've abstracted this notion of, in the intermediate representation, we've got a notion of an outer for loop and an inner for loop. In OpenCL and CUDA, those for loops disappear. Remember? All we're left with is the body of the inner part of those nested loops. In Arca, we put the for loops back in. We demand that the programmer inserts those for loops back in. Originally, in the intermediate representation, just threw in a macro. Because once we've got those for loops back in, we can transmute them into OpenMP loops, or we can get rid of them for OpenCL or CUDA. So it gives us a way to actually generate code that's either OpenMP, OpenCL, or CUDA. And that sort of explains that. But it was a bit clunky to program. So what we did is we let you now, in the OKL and OFL kernel language, just write for loops. And then tag for loops as to whether they're going to be outer or inner for loops. And that would be what a triple nested partition for loop could look like. Okay? So it looks a lot like serial code. There's no hidden for loops which are implicitly born by the thread array, because we produce that code automatically, right? So if you write the kernel with the OKL language, you'll have to specify it's a kernel, and then you specify the for loops just as you would normally. It's a little bit nicer than pragmas, where you're saying, I hate pragmas in code, directives in code. I can't read it very well because it sort of takes you out of the code. It's like, I think, if you read a play, including the stage instructions, it's not the same as just reading, as watching the play, right? There's always this distraction of what's actually happening with those stage instructions. So this is a simplified way to program kernels. You still need to identify those outer loops and those inner loops. But at least the structure's there, yes.
What is the workflow? We write this code, we compile it, and there is recompile it.
So it's much the same as the CUDA or OpenCL workflow. Sort of a hybrid between the two of them. I've got an example. Here's an example. Adding two vectors. So you're going to create some host memory, host arrays. You're going to populate the host arrays. We'll need a device, some kernels, and some memory objects. You'll set up the device. You'll allocate some space on the device. You'll copy some data from the host to the device. You'll build the kernel. We still have to do that, right? Because we don't know exactly what the back-end platform is. In some sense, it's OpenCL, but worse, because it's all the stuff in OpenCL, plus the option to choose OpenCL, OpenMP, CUDA, right? We do have kernel functors in C++. There's a different interface in C, so you can actually call the kernels as you'd expect. Notice, because we have for loops explicitly described in the kernel, we don't need to set the thread array at this point, because the thread array dimensions are extracted from the kernel source. That's simplified. And then finally, we need to copy data back. And this is the kernel code, where we've just tiled the for loop with groups of 15, or sorry, 16, okay? And because that upper bound to that for loop is known, all code's generated with, so we can extract that, and that gets fed into the dimensions of the thread array. So in some sense, we've simplified the host code, and we've made the device code a little bit more transparent as to exactly how you should think about this kernel code. There's no hidden parallel for loops. They're all exposed. Right, and we have shorthand. You can just tile an array with the tile command in that last entry in the for loop. We're cognizant of the limited support for Fortran in accelerators, so we've provided a Fortran interface, a Fortran API, and a Fortran kernel language. Kind of the same thing. Okay? But that's still a pain in the ass, because we had to manually move data around. So because we've got a parser, we've extracted an AST, an abstract syntax tree for the kernels. We know the data dependency of the kernels, so we can then engage in automated data movement. So if you're a Ninja programmer, you would use OpenCL or CUDA. You wouldn't probably necessarily need to deal with this stuff. But if you're an expert, then you might want to use the IR. If you're a casual programmer, you probably use the CPU. So there's lots of things here. What we did is we either took advantage of the CUDA unified virtual address space, which unifies the space of memory on the device and the host, and we emulated that in OpenCL, and we provide support for that in OpenMP. And we actually have managed data so that if you manage arrays, so if you allocate an array, we can get rid of some memory copies and simplify the code. So that now we still have to set up a device, we still have to build a kernel at runtime, and we don't have to explicitly move data, because when we launch that kernel, we'll look at the dependencies of the arguments and decide whether we have to move data or not. If you trust us to do your data movement, we can do that for you. It's pretty simplified. We're gradually moving all this nonsense from OpenCL and CUDA behind the scenes. We're trying to automate this process so it becomes as close to regular code as possible. Eventually, we'll build an occupancy compiler, OCC, which will mean that you don't even have to build kernel from source. So we'll get rid of that line. The trouble is we've done most of the low-hanging fruit, the data movement, the stuff like that. We're working up to more and more complicated things. Next, we have the parser, so we'll use that to build a compiler. That means you don't have to build kernel from source. It'll be just extracted from the regular source by the occupancy compiler. Okay? We have already a default device, so you don't even need to set up the device. The next step, and this is the part of which is research, is if we look at this kernel, the only thing that's non-standard is the annotation that this is a kernel. You see that? The only extra keyword there is kernel. The thing we have to do is analyze the dependencies of the loop iterations and say whether it's possible to turn this automatically into, or is it possible to tile this automatically? And for some kernels, we can already do this. But that's still a work in progress. So we have a kernel and a Fortran version of this kernel language, which is basically serial code that gets put through our parsers a couple of times, where we analyze the code, can we partition this loop? If we can partition this loop, we'll generate the code, and that gets fed to the IR. Yes?
Just curious about the parser. Is that an LLVM based or
The question is, he's curious about the parser. What kind of parser do we use? Did we use rows? Did we use LLVM? Did we use one of the existing parsers or compilers? We did this very quickly. And the learning curve for LLVM and rows is actually quite steep. And neither of them, as far as I'm aware, provides good manipulation tools for manipulating the abstract syntax trees they generate. So my student, who's a rather remarkable programmer, built his own. He's pulling his hair out in the back. He built his own. It's not that difficult.
Isn't that the principal thing that one would just advise against?
Oh, absolutely, and I did.
Does it have at least an LLVM compatible interface?
No. But
what if he gets hit by a bus tomorrow?
That would be very unfortunate. Yeah. Hold on a second. So actually, I have an issue with the people behind LLVM and rows that, in some sense, and I've queried my friends in computer science at Rice, so Keith Cooper and Malacromi and these guys, and I think it's a bad reflection on those tools that they aren't more usable and aren't more accessible for this kind of work that we had to do. So I would actually push back and say that that's a problem with LLVM and rows and all the other variants, that they aren't easier to deal with. So he did this quickly. We will revisit this and do this via LLVM or rows later on. But this is proof of concept. But I think it's interesting that computer scientists said, why didn't you use LLVM? And I think the answer is because computer scientists haven't made LLVM usable. So I would love to avoid that. I thought it was yak shaving of the nth order, but we did it, or he did it. And this is why it may be a little bit more advanced than OpenCL and CUDA in terms of what we can do. Because we're not straitjacketed into what you can do with those tools. Does that answer your questions?
Yeah, I asked that because I'm the one who write a parser. I use a lexan to translate our domain-specific language. And the only problem with rolling your own parser is when you start adding new features into the, like over the time, then your own parser becomes too much complicated. So
this is pretty straightforward, and it's all downloadable.
Yeah.
So and it can parse all the standard headers and everything that we've thrown at it. Doesn't mean it's perfect, but it's proof of concept. What we really want to do is we don't want to be in the business of building this and maintaining this for the community. We just want to show what's possible. So this is why it's sort of duct taped together just to get to where we want to get. And then the computer scientists can maybe help us out and do this in a sort of computer sciencey way, right? So just to reiterate, eventually we get rid of this. We'll have some default device setup, and it suddenly looks a lot like regular C or C++. Isn't that the goal? That we don't have to sit here for 3 hours and learn the intricacies of loop partitioning, because that's essentially most people's goal is not to partition loops. Right. So this is the automatic kernel. So basically it will generate this code, readable code as well, from lots of different parsers through this. Okay. So let me just quickly show you some things we've been able to do with this infrastructure. We've built industrial strength. Yes, hello.
I was wondering, before we get into the applications, what are the inherent limitations if one wants to stick to the generic interface?
So things that we didn't do that appear in CUDA. Is that a question?
Okay, so it's OpenCL.
It's the kind of the intersection of CUDA, OpenCL, OpenMP, with some things that appear in one of them would be that don't appear, and other things would be emulated in some manner. So what does shared memory mean in OpenMP? Right. So we've had to sort of produce the analog.
Well, so what does it mean? You do some staging? Because that's additional useless work.
No. It just means that a shared array is an array where it's just a regular array that is local in scope to the inside the outer loops, for instance. So all those decisions had to be made, and this sort of mishmash of stuff had to come together in a coherent way.
But in practice, then, that would mean that if somebody really wants performance, then at least the CPU-targeted code and the GPU targeting code has to be different, even with the generic interface.
That's the nature of these results. I'll show you in a second. But the key is that there's one front interface, and then you have the option to provide one or more kernels for each platform you choose.
Okay. And there is no plan to support some kind of extensions?
Well, that's the next step of building the compiler, which type of extensions you were talking about?
For instance, some algorithms will just die without shuffle.
Sure, we could add shuffle. But
shuffle, in fact, is supported by AMD too. It's just that they never bothered to expose it.
Right. So if there's demand, if there's pull from the people using it, we'll add it. Typically, features are not difficult to add. It's not a tricky thing to do. We just have to figure out an analog across the different APIs.
But there is no plan to add to enable perhaps some fancy C++ mechanism.
Yes, that's in
to
the
provide some extensions.
So
where I define the operator somehow.
Yeah. We're looking at lambdas. Yeah. So it depends. It has to be a pull from the user group, and the Raja group at Livermore is interested in that. So that's on the roadmap. Yeah. So it depends on, if people want it, then we'll make it happen. Usually it's very quickly. Yeah. So we have industrial strength high-order finite difference codes. So those of you who are familiar with finite difference codes, you'd be kind of shocked that the industrial strength might involve 25.3D solvers with second order in time central differencing, which is kind of crazy, weird thing that they actually use in production in industrial seismic. So we have codes for that. We have spectral elements codes. There was a question about spectral elements earlier. We have elliptic codes. We have hyperbolic codes, parabolic codes, all set up. Discontinuous Galerkin for numerous applications, lattice-Boltzmann methods, algebraic multigrid solvers, Monte Carlo solvers based on mini-apps from Argonne and others. We have tsunami solvers. So one of my graduate students from India, he was pretty close to the coast when the Indian Ocean tsunami hit, and this motivated him to say, how fast can we do this? Not on a supercomputer, but on a workstation that could be ubiquitous. That's a reasonable question, and he got it down to probably a minute or two just on a workstation to do a high-fidelity modeling. The limiting factor there is actually the bathymetry available for the ocean and the near shore. And we get pretty good performance. So we have one implementation, we get good performance on the GPUs, and we have reasonable performance on the CPUs. There are some spikes in performance on the CPUs, so the horizontal axis is the polynomial degree used for reconstruction, blah, 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 blah. But that involves a number of threads that depends on the polynomial degree, and when that happens to be a multiple of 8, we get excellent vectorization from the Intel OpenCL vectorizer. If they're not a multiple of 8, then we get really poor performance. So we can always pad the number of threads. We talked about padding arrays earlier, but you can also pad threads and get threads to do dummy work and then force work through the vectorizer. That was one implementation that got pretty good performance across multiple platforms.
Is that just using like a second order DG method?
No, that's fourth, it's up to sixth order there. I mean, that's what we do. That's the bread and butter. That's my day job, right? So we had to make this run fast. This is the only DG code that runs higher than first order for this problem. There are some challenges in the bathymetry in the shadow and modeling the flow in the shallows near the north part of the Indian coast. Let's see what else we got. We have spectral element code. This is actually a fascinating application. I wish I had time to talk. Well, I could talk about this at great length, but Rice is near the Houston Medical Center, and we have doctors over there who are doing things like modeling laser-based treatments for tumors. So we actually have this high-order finite element modeling tool for modeling the impact of what is it called? Magnetic resonance guided institutional thermal therapy. Basically, take a patient with a brain tumor, drill a hole in the skull, insert a fiber optic catheter into the brain, light it up with a laser, heat it. The questions the surgeons have is how long should you apply the therapy, at what power to maximize the tumor death, minimize the collateral damage. So it's an optimization problem. The original code was a finite element code based on a package. It took hours and hours to run one instance. We can run it in 17 seconds, so you can run multiple iterations of an optimization loop to actually figure out how you should form the therapy. So that made a substantial difference into the capabilities. Let's see what else we got. We've done some Rodinia benchmarks. And there's an interesting thing that happens when you unleash a very talented grad student on a set of benchmarks. It turns out you're not really testing to see whether the framework is working as you'd hope. You're testing to see how well the graduate student transmutes code into the portable interface so that it works across multiple different platforms. So I'm not benchmarking Ocker in a sense. Ocker is just a sort of semi-transparent layer into all these different interfaces. What I'm testing is how good is my student at optimizing code. And in general, he's better at writing code than the implementations of the benchmarks that appear on the web. So that's hard to gauge the success of Ocker through this. So if you look at the original CUDA for this example, one of the Rodinia benchmarks, you'll see the original CUDA. This is it running inside Ocker because he couldn't leave it alone, and he improved it as he ported it over to Ocker. Same answers, better implementation, better performance. So it's a standard question about how exactly do you benchmark this kind of thing. Breadth first search. Here's an example where the same code running in CUDA is substantially faster than the same code running in OpenCL on the same device from NVIDIA, which comes back to a question earlier about the relative performance of NVIDIA's CUDA and OpenCL. It has been well known that NVIDIA's CUDA can be a lot better than NVIDIA's OpenCL. Now, the really puzzling thing here is that both NVIDIA's CUDA and OpenCL use LLVM in the background. So something different happens in the transmutation of, or transcoding of the kernels into the LLVM backend. I've noticed in the most recent CUDA, those differences have, most recent release, those differences have leveled out somewhat. Yes?
Regarding the OpenCL CUDA comparison, that is with the smallest or greatest common denominator feature set, nothing that is unsupported used.
Yeah, so that's using our Ocker's support is sufficiently rich that it's the same. It's covered in both for these benchmarks.
And you get that big of a difference.
Yeah. Fascinating, huh?
Oh, I have to say,
But the funny thing is,
I had a bad opinion, but now I have a really bad opinion because that looks like crippling.
well,
That looks like
I don't think it's that straightforward.
Or just awful negligence.
I don't think it's that straightforward. I think it's a matter of resources. Before, there was an interesting thing in about 2010. I had a CUDA and separate handwritten CUDA and OpenCL implementation of something, like one of my simulators. And the OpenCL was 10% faster because at that point, OpenCL was using LLVM in the back end, and CUDA was using Open64, I think, in the back end. And the LLVM would come up with a better schedule for the tasks. I was told it was a bug. But now things have some switched around. When they switched to LLVM, they found 20 to 30% boost, or 10 to 20% boost, but somehow the OpenCL didn't quite stay up. Right, applications. Monte Carlo solver from Argonne. Again, the thing we wanted to make sure is that Occa didn't get in the way of the CPU performance, and it didn't get in the way. Didn't get way, maybe a 5% dip in the performance. I'm not sure exactly why that was. We sometimes run into this issue that CPU kernels code you write for a CPU can sometimes work really well on a GPU, but sometimes it just tanks. So in some instance, and in this case, this highly tuned finite difference code, there's all sorts of tricks you can do for finite difference on CPUs that don't really apply on GPUs. So if you do that on the CPU, then you can impact the GPU performance and vice versa. So this is a finite difference code which is optimized for the CPU and not optimized for the GPU, same code. And you can see that we would pretty much don't lose any performance, but if you run it on the GPU, you can lose performance. Actually, no, I'll take it back. This is all on the CPU, and this is the GPU-optimized kernel, and it doesn't do as well as the CPU-optimized kernel, as you kind of expect. And you get the similar kind of performance, similar kind of issue on the GPU. But having said that, even if you use the CPU kernel on the GPU, you're within a factor of 2. Basically, it comes back to this point that the issue of optimizing for the CPU and GPU they're not that different nowadays. As long as you manage data locality in a very good, well, carefully, then you can still get reasonable cross-platform performance. So, just to summarize, we have a many-core device abstraction, unified kernel language, automation, we're trying to automate data movement, we're trying to automate the production of kernels. And we've examined the performance over many different numerical methods, and we're getting good performance across multiple different backends. And we've got an example on the web page. You can go and look at it, and it'll show you the full implementation of the Jacobi iterator running in Occa. Here's the side-by-side. You have the serial code, the CUDA code, the OpenCL code. There's the intermediate representation. Oops. And this is the Occa kernel language. And if we look at the serial code and compare it with the serial kernel, so the OKL kernel versus serial kernel, the only difference you really see is we've manually partitioned the for loops and we've tagged the for loops. And more or less everything else survives. It looks just like regular C code, just with a few extra tags. So we have a lightweight API, multiple front ends, works with multiple back ends. We have a version for Windows. I'm not sure if we're supporting that because we don't like Windows. We've tested on multiple different devices. We've got portability and sometimes performance, portable performance for multiple different discretizations. And we're trying to minimize exposure, not just to vendor lock, but also model lock. You don't want to get necessarily too close to the threading model. You want to be portable across multiple threading models. There's a report, a GitHub, and I'll end the story there. Thank you very much. So if you do have any questions, now's time to ask. Yes?
Can we do memory allocation from within a kernel in CUDA?
Oh, I've not done that. I usually just have stack arrays if I'm going to have some local register arrays. I'm going to look at, you can use new or...
Well, you can use malloc within the kernel, but...
It should be very limited. And it will be local to the thread, right?
Yes.
Yeah.
Well, no, I think the memory will be allocated as usual.
You can allocate device memory? Yeah, I think so. That would be crazy dangerous.
So I haven't seen any codes actually using that, but it is available out there.
That, I think that's up there with the dynamic parallelism. I think it's something that's there, but I would be very leery of it.
Yeah,
so can you call them in dynamic parallelism a kernel recursively with memory allocation and just point the device?
Yes, I think this is one of the main reasons to expose it, right? So when you're trying to do a dynamic parallelism and you're trying to spawn a new kernel, you want to allocate some memory for that in global memory, because if it's local memory, then this kernel won't be able to access it. That's why I think it's allocated in global memory.
So how fast is it allocated?
Yeah, it's slower. I mean, it's not fast, I think, so there are some performance considerations, right? But we might have some benchmarks or something with that.
Because the only way to return some value is either through the return value or some global memory.
Well, you could always do it through global memory, yeah. That's pretty much the only avenue out.
Yeah, I mean, you can pre-allocate the memory, in advance and try to handle all the pointers there. So it's usually the most, the best way to handle it. But in some cases, I mean, if you cannot, if each thread needs to allocate its own memory space for some reason, I don't know.
So I've been doing this for 8 years, and I've avoided any sort of dynamic stuff like that. I mean, I usually have very carefully predetermined static tasks with static array, predetermined arrays. You can apparently do really stupid things if you want to. So just think about it. So in a typical computation, I might have a million threads that get executed more. Because if I have a thread per update of a kernel of a compute node, of a node in a finite difference lattice or a spectral element lattice or whatever lattice it is, I might have one thread for each of those data points. So I have computations where I've had 50 billion degrees of freedom. So I might have on the order of 10 billion threads. You have to be very careful and cognizant of what you're going to get each thread to do. And if you give them the freedom of each of them can allocate some arrays, and it could get very messy very quickly. But maybe that's my lack of imagination.
My question is regarding performance portability with regard to the way we store data on the CPU and GPU. For example, when we do optimization for the GPU, we try to congest data in such a way that a thread takes one index and it will be coalesced. If I use that kind of scheme for the CPU, I'll have fault sharing problem. So is there a plan in Orca to automatically do that for me?
We have some rudimentary ideas, but it's more about data layout in terms of, you can think about whether, so if you have an array, which is the fastest running index? Do you want to be able to permute the layout and then try different layouts to see which will be the fastest way to access this data? It might be different on different devices. So the fancy way of looking at this is array of struct of arrays. But that's really just looking at what's fastest running in memory. So you might choose column major on one device, row major on another device. Sort of that facility is there so we can introduce a permutation of the array indices. So some rudimentary support is there or being developed. But that's not something we've yet exposed in the production version. But we're paying attention to that. Yes.
Maybe I cannot follow you well, but in your example with this Jacobi, with this CUDA, in one dimension, when it is straightforward to understand the thread, you just took a look. But in this Jacobi example, you have to kill the thread. You have to choose this thread. Maybe can you explain a little bit so that I can follow it?
Okay, so in 1D, we just had we made a decision that we would have a one-dimensional array of threads, and we'd chunk it into blocks of threads, and each block of thread would handle a block of the vector, and each thread would handle one entry in that vector. Then we have a little bit of an issue at the end of the array because we'd have more threads than we had entries, so we would guard against out-of-bounds write. It's much the same in 2D, where we decided to block the nodes in the finite difference array into blocks. And then we would decide we would have one thread per node in that block. Okay? We didn't have to do that. We could have had a one-dimensional array of threads and use some modular arithmetic to find out where we are in a two-dimensional, right. But we just used the fact that we had this multi-dimensional thread rank in order to be able to find out where we are in a multi-dimensional array, a finite difference array.
So I can, if I understand you well, then you can do the same similar thing to this 1D, but just calculate explicitly. Okay.
Yeah. So I just in that example I exposed a couple of things. One was multi-dimensional thread arrays. The other was the reduction. That was using shared memory. That was the point of that example.
How about three-dimensional?
Yep, same thing. You can have a three-dimensional block of threads and a three-dimensional grid of blocks. And once you've got 6 coordinates, you can find out where you are in the global array of global three-dimensional volume of threads.